So first let's look at question number 1. So question number 1 is asking what is a time slice? And the correct answer is that the time period for which a thread is scheduled on the processor without interruption is called the time slice. Suppose this is the processor, and let's say that there are multiple threads which are waiting to be scheduled. So they'll all be put into a queue which is called the ready queue. And what the processor will do is it will pick one thread at a time and execute it. It will continue to execute this particular thread which is at the head of the queue until the time slice expires. Right after the time slice is over, it's going to put it at the end of the queue and pick up the next thread for execution. Of course, there are other cases wherein a thread may make a blocking call, maybe it does some disk access or some network access, because of which it is moved out of the processor. But barring those, if it does not make any blocking calls or does not yield, then it will continue to execute to do the computations until the time slice expires. Okay, so question 2 is asking the dynamic state of the thread that must be saved on a context switch includes what? Does it include the registers, the data in the cache, the data in its heap, or its code? Now the data in the registers is required again when the thread is scheduled next time. Suppose that it is executing some instruction, add R110, and then later it's supposed to execute another instruction, let's say add R120, and let's say that it got scheduled out, its time slice expired after it had executed add R110. Right, so next time when it is scheduled, it's going to execute this instruction add R120, and it's going to expect the contents that were there when the previous instruction was executed to be there in the register R1. Right, therefore what must happen is that R1 must contain the same contents that were there when the thread was scheduled out. Now every thread has to use the registers, so the next thread that is scheduled in is going to use all the registers, and therefore it is going to override the value of R1, register R1. Hence it is necessary for the thread to save the state of all the registers when the context switch is done and restore it back when it is scheduled next time. When it comes to cache, note that the cache can always be refilled. There may be some overheads in refilling the cache again, but that's fine. So when a new thread comes, it's going to start accessing its own data and it may replace the contents of the cache, but the old cache contents will be written to the memory, so the memory will be kept consistent, and next time when this thread loads again, the cache will be refilled again. And note that the heap and the code are kept in main memory, therefore there is no need to store these on a context switch. Now let's look at question number 3. What it's asking is that what is the value of P printed over here when OMP numthreads is equal to 2. Right, so what will happen is that first there is a call being made to OMP get numthreads outside. So this is happening outside the hash pragma OMP parallel, so it's outside the parallel region. So remember that the fork happens when the hash pragma OMP parallel region is encountered. Therefore, at this point in time, there is only one thread which is executing. Hence, OMP get numthreads will return 1 over here. Right, so we will get T equal to 1, and then the parallel region starts. Inside the parallel region, what we are storing in X is OMP get numthreads. So at this point of time, there are 2 threads executing, and X is a private variable, so both of them will get the value 2 in X. And finally, at this point in time, one of these threads is going to execute hash pragma OMP single, and it's going to add the content of X to T. But the value of X is same for both the threads, and so what it will end up adding to T is 2. Therefore, T will get the value 3. Right, and that's what will be printed when you print T. Hence the correct answer is 3. And question number 4. Which of the following techniques can be used to resolve false sharing issues? Right, so the first is explicitly declare the data to be shared. Well, that has nothing to do with false sharing. The second option is use critical sections to guard operations on the data. That is something that we should do anyways for shared data. Either use critical sections or hash pragma atomic. And the third option is pad the data being accessed with some dummy data. Now let's recall what is false sharing, right? So the problem that happens is that the cache is composed of cache lines, and if one thread, let's say thread 1, is working on some variable, let's say it's here in the cache line, and now let's say that the second thread is working on a variable which is in the same cache line. In this case, what happens is that whenever thread 1 and thread 2 are accessing their variables respectively, then the cache coherence protocol kicks in, and every time these values are updated, either the other cache has to be invalidated or updated, right? And therefore there are overheads of the cache coherence protocol which cause a slowdown in performance. So the main cause of the problem is the fact that both these variables are residing in the same cache line. So if you have an array, let's say ARR of size, let's say 4, and there are 4 threads, and thread 0 is working on ARR 0, thread 1 is working on ARR 1, and so on, then you are going to run into the false sharing issue. Therefore, typically what you should do is that you should pad the data. So you can define a structure which basically consists of the ARR element that you want to work on. Let's say it's of type integer, and you can use some padding, right? Alright, and then we should use an array of the struct x, right? So what this will ensure is that in the cache, so since the size of x is large, right, it consists of 8 integers, it will ensure that if this is where the ARR for, let's say, x0 resides, then the subsequent memory is not being utilized, right? So in other words, it ensures that you don't have more than one element of interest in each cache line. Now let's have a look at question number 5. So it's asking what is the output of the following code if OMP numthreads is equal to 4. So what's happening in this code is that there is a parallel region, and within the parallel region there is a for loop that is being distributed amongst the threads, and the schedule that is specified is static 10. In this case, the loop will be distributed in units of 10. So the loop is running from 0 to 99. So there are 100 iterations of the loop, and these will be distributed in blocks of 10 because we have said the unit of operation is 10 iterations at a time. Therefore, we will divide 100 by 10, and what we get is that there will be 10 blocks that are to be distributed. Right? Each block is containing 10 iterations. So now how do these 10 blocks get distributed amongst the 4 threads? So they get distributed equally, and the first few threads may get one extra block. So in this case, if we divide 10 by 4, we get 2.5. What this means is that all the 4 threads will get 2 blocks each, and in addition the first 2 threads will get one additional block, so that the total becomes 10. And now what happens in the code is that we check if t is equal to 3. What is t? T is OMP get thread num. So the third thread is going to print the value of x of t. And what is the value of x of t? Well, x of t is doing nothing but storing the number of iterations worked on by thread number t. Right? So t stores the thread number, and what you're doing inside this loop is you're incrementing xt. Therefore, at the end, x of 0 will store the number of iterations worked on by thread number 0, x of 1 will store the number of iterations worked on by thread number 1, and so on. So what is the number of iterations worked on by thread number 3? In this case it is 20, since there are 2 blocks that are assigned to thread 3. Next we look at question number 6. In the following code, the goal is to print the sum of IDs of all the threads. Where can a delay be introduced to highlight the race condition? So there is a parallel region, so all the threads are going to execute this part of the code. And what each thread will do is it will get the thread number, store it in the variable x, and add that to the shared variable t. Right? And in the end we are printing t. And what is the problem here? The problem here is that x itself is also shared. Right? That's what is causing the problem. So how can we highlight this problem? So what we can do is we can introduce a wait at S2. Why does that work? So what will happen is that if we introduce a large delay at S2, then what's going to happen is that all the threads are going to come and execute the statement x equal to omp get thread num. So let's say that you have two threads, thread 0 and thread 1, right? So thread 0 is going to set x to 0, thread 1 is going to set x to 1, and let's say that thread 0 executes first, followed by thread 1, right? So thread 0 does not go and increment t because it's entered a long wait at S2. In the meanwhile, thread 1 also sets x to 1, and after that, both of them enter the wait. Once they finish the wait, what is the value of x? The value of x is going to be the thread number of the last thread that executed this statement, x equal to omp get thread num. Right? So if thread 1 executed it last, then x is going to be 1, and if thread 0 executed it last, it's going to be 0. So when we come to the statement t plus equal to x, both the threads try to add the value of x to t, and in this case, if let's say thread 1 executed x equal to omp get thread num last, then the value of x is 1, and both the threads are seeing the same value x equal to 1. Therefore, both of the threads will add 1 to variable t, and hence the value of variable t will be 2. Had thread 0 executed x equal to omp get thread num last, in that case the value of x would have been 0, and both of the threads would have tried to add 0 to t, and the final value of t would be 0. Thus in either case we do not get the correct answer, where we wanted the value to be 0 plus 1 equal to 1. Therefore S2 is the right place to introduce the long wait. In question number 7, what is wrong with the following code when run with omp num threads equal to 4 if the expected output is s equal to 2? So what are we trying to do over here? S is a shared variable and there's a parallel region over here. So this entire thing is inside a parallel region. And then one thread is supposed to go and execute this part of the code s++ because it's inside a hash pragma omp single. And the master thread is going to execute this code s++, which is inside hash pragma omp master. And finally, some thread is going to print the value of s. Right? S is a shared variable. Alright, so what can go wrong over here? Well, first of all, note that we have a no wait condition over here. What that means is that one thread is going to come and start executing this, but the other threads are not bound to wait over here. They can go ahead and start executing the instructions after this hash pragma omp single block. And therefore what may happen is that while one thread is trying to increment s over here, the master thread might be trying to increment s over here. And due to the race condition, it might happen that s may not get incremented twice. Even if this does not happen, there is another problem over here, that is that if the master thread is trying to increment s over here, at the same time another thread could be executing this hash pragma omp single and therefore might be printing at the same time. And what may happen is that the thread may print the value of s before the master has updated the value of s. Hence the correct answer in this case is both A and B. In question number 8, we are asked amongst vector-vector operations, matrix-vector operations and matrix-matrix operations, which will benefit from spatial locality and which will benefit from temporal locality of the code in the presence of a cache. It's important to note that in vector-vector operations, we use each element only once. Therefore, they involve the same or more memory operations than the number of compute operations. And moreover, they stream the data and thus benefit from spatial locality, right? So if you're doing, let's say, a dot product, then you're streaming two vectors and you're not reusing the data. Now, when we come to matrix vector operations, such as matrix vector multiply, we use each element of the matrix only once. So they also involve the same or more memory operations than the number of compute operations. And moreover, we stream the matrix. So these operations also benefit from spatial locality, because once you load some data, some of the following elements are automatically loaded in the cache line. When we talk about matrix-matrix operations, note that these involve more computations than the memory operations. Therefore, in these operations, data that is loaded once can be reused. And a good example of that is what we studied in class, which is block matrix multiply. Therefore, they benefit from temporal locality because we are reusing the data once we load it. Now, since matrices are stored contiguously, they benefit from spatial locality as well. Therefore, the correct answer is that all the operations benefit from spatial locality and matrix multiply benefits from temporal locality of the data. Now let's have a look at question number 9. So we are given two threads in OpenMP code and they are trying to execute the following instructions. Thread 1 is trying to increment head and tail and thread 2 is trying to decrement head and tail. And we are given two codes and we want to know that which of these is correct. Now there is actually no problem with code 5.1, it will work absolutely fine, but there is an issue with code 5.2. What is the issue? So the problem is that suppose that thread 1 enters critical section 1, right? And at the same time thread 2 enters critical section 2. Then the code is going to hang. Why? Because thread 1 will keep waiting over here wanting to get into critical section 2, and thread 2 in the meanwhile is waiting over here trying to get into critical section 1. It is inside critical section 2, right? So it is not gotten out of critical section 2, therefore thread number 1 cannot get into critical section 2, and similarly thread number 2 cannot get into critical section 1 because thread 1 is already inside critical section 1, right? So there is a problem with code 5.2. Hence code 5.1 is the appropriate code. Let's have a look at question number 10 now. So the question is asking what is the maximum collapse level that can be specified with the hash pragma OMP for in the following code in order to give the same result as the sequential code. Right, so look at index k carefully. What you note is that ARR ijkl is dependent on ARR ijk minus 10l. Now what will happen in the sequential code? The way these loops are organized in the sequential code, when you update ARR ijkl, ARR ijk minus 10l has already been updated. Therefore, you are using the new value of ARR ijk minus 10l. Now, what happens if we specify collapse level to be 3 or more? So, in that case, what will happen is that this for loop for k will also get distributed amongst the threads. And when that happens, what might happen is that while some thread is trying to update ARR ijkl, another thread may be responsible for updating ARR ijk minus 10l, right? Because the k loop has also been distributed. And now we do not know which thread is going to execute first. Therefore, what may happen is that you may end up using the older value of ARR ijk minus 10l, which has not been updated. Hence, we can only specify a collapse level of 2.